VLAN, a virtual local area network, VLAN, is a method of logically dividing a single physical network switch into multiple distinct, isolated networks, even if the devices are connected to the same physical hardware. Each VLAN functions as its own separate network, or broadcast domain, which enhances network security, performance, and manageability. Key functions and benefits: network segmentation. VLANs allow network administrators to group devices based on logical factors, like department, function, or security level, rather than physical location. For example, computers in the finance department can be on a separate VLAN from a guest Wi-Fi network. Improved security. By isolating traffic, VLANs prevent devices in one segment from directly communicating with devices in another, which restricts unauthorized access to sensitive data and minimizes the spread of malware within the network. Reduced broadcast traffic. In a traditional large network, broadcast messages, traffic sent to all devices, can consume significant bandwidth and slow down performance. VLANs confine broadcast traffic within each smaller virtual segment, thus reducing network congestion. Cost-effective and flexible, VLANs allow organizations to create multiple networks without the need for additional physical switches or dedicated cabling, making network design more adaptable and cost-efficient. Simplified administration. When a user moves to a new physical location, their device can remain in the same logical VLAN with just a configuration change on the switch port, rather than requiring physical rewiring. How VLANs work. VLANs operate at Layer 2, the data link layer, of the OSI model using an industry standard called IEEE 802.1 Quetzales. VLAN tagging. When data, an Ethernet frame, is sent between VLAN-aware devices, a special 4-byte tag containing a unique VLAN ID is inserted into the frame's header. This ID, a number between 1 and 4094, tells network switches and routers which specific virtual network the packet belongs to. Switch ports. Ports on a network switch are configured in different ways. Access ports, used for connecting end-user devices, computers, printers, IP phones, and carry traffic for only a single, untagged VLAN. Trunk ports, used to connect switches to other switches or routers. They carry traffic for multiple tagged VLANs over a single physical link, acting as a highway for all inter-VLAN data. Inter-VLAN routing, to allow devices on different VLANs to communicate, example an employee accessing a server in another VLAN, a Layer 3 device like a router or Layer 3 switch is needed to route traffic between the different virtual networks. In essence, a VLAN acts like an invisible wall within a switch, keeping different groups of devices separate and organized, even when they share the same physical infrastructure. VLANs are a foundational technology in modern networking and are used extensively in various environments to manage traffic, enhance security, and simplify administration. Common applications and scenarios include corporate and enterprise environments. VLANs are ubiquitous in businesses of all sizes to segment the network based on function, department, or security requirements. Departmental separation, isolating traffic from different departments, such as human resources, finance, sales, and engineering, prevents employees in one group from accessing data and systems intended for another. Secure guest access, organizations use a dedicated guest VLAN to provide internet access to visitors and personal devices, BYOD, while completely isolating them from the internal corporate network and sensitive data. Voice over IP, VoIP, and video, real-time voice and video traffic requires consistent, low-latency communication. A dedicated voice VLAN ensures this traffic is prioritized, using quality of service, or QoS, and unaffected by regular data traffic congestion. Network management, a separate management VLAN is used to securely manage network infrastructure devices like switches, routers, and servers, restricting access to administrative interfaces to authorized personnel only. Data centers and cloud services. In large-scale environments, VLANs are essential for managing complex traffic and multi-tenancy. Server segmentation, traffic to and from web servers, database servers, and storage area networks, SANs, is separated into distinct VLANs to control access, minimize security risks, and improve performance. Multi-tenant isolation, cloud computing providers and shared office spaces use VLANs to virtually separate the networks of different customers or tenants, ensuring that each client's environment is isolated and secure from others using the shared physical infrastructure. Virtualization, in environments with many virtual machines, VMS, VLANs are heavily used to manage communication between VMS and different physical hosts, segmenting the traffic for security and performance. Specialized and industrial environments. VLAN technology is also applied in operational technology, OT, and industrial control systems, ICS. Industrial control systems, ICS. In manufacturing or automation facilities, VLAN separate critical, time-sensitive control system traffic, like PLCs and sensors, from less critical monitoring or IT data, ensuring reliability and security. Healthcare and finance, industries with strict compliance and data protection regulations, like HIPAA or PCI standards, use VLANs to enforce strict isolation of sensitive records, example patient data or financial transactions. Smart homes and IoT, even in residential or small office settings, VLANs can be used to segment smart devices, thermostats, security cameras, printers, etc., onto a separate network, protecting primary computers and personal data if an IoT device is compromised. VLAN 802.1q frame structure. The IEEE 802.1q standard works by inserting a 4-byte, 32-bit tag into the original Ethernet frame, right between the source MAC address and the original EtherType/length field. This process increases the maximum Ethernet frame size from 1518 bytes to 1522 bytes. This 4-byte tag is comprised of two main parts, the Tag Protocol Identifier, TPID, and the Tag Control Information, TCI. Position of the 802.1q tag field size, bytes, description destination MAC address 6 the MAC address of the destination device. Source MAC address 6 the MAC address of the sending device. 802.1q tag for the inserted VLAN information. Original EtherType/length to the original EtherType or length of the data field. Data and padding 46 to 1500 the actual data payload. Frame check sequence, FCS, for error detection field, recalculated after tagging. Structure of the 802.1q tag field. The 4-byte VLAN tag itself is broken down into 4 distinct fields: size field description, bits, bytes, tag protocol identifier. A fixed value of 0x8100 is used to identify the TPID162 frame as an IEEE 802.1q tagged frame. Any device that does not understand 0x8100 will simply discard the frame, ensuring compatibility. Priority code point. This field supports IEEE 802.1p quality of service BCP3, QoS. It allows for 8 different priority levels, 0 to 7, enabling time-sensitive traffic like VoIP to be given preferential treatment during network congestion. Drop eligible indicator. This single bit is used to indicate whether the frame DEI1 is eligible to be dropped in the presence of heavy network congestion. VLAN identifier. This is the core component for VLANs. It uniquely identifies the VLAN to which the frame belongs. The 12 bits allow for 4096 VID 12 possible VLAN IDs, 0 to 4095, with IDs 0 and 4095 typically reserved, leaving 1 to 4094 available for use. The PCP, DEI, and VID fields are often collectively referred to as the Tag Control Information, TCI, field. When a frame is tagged, the transmitting switch recalculates the frame check sequence, FCS, to ensure error detection still works for the modified frame.